Okay, the yellow sheet I gave you tells you the story about angular velocity versus linear velocity. So again, angular velocity, imagine you have some type of a vehicle, bicycle, roller skates, car, whatever, that has wheels that are turning in a circle that propel the vehicle in a straight line forward. Linear velocity is going to be your usual velocity, the miles per hour, feet per second, meters per second, that kind of thing. Angular velocity is going to be the speed of the rotation of the wheels on the vehicle. And again, you're looking for any one of your angular type of value or of units on top over some unit at a time on the bottom to establish that it's an angular velocity. Omega is the typical thing we use. It looks like a fancy W. It's actually, it's like a little O with some arms. And the capital version of that, it looks like this, just in case you're curious. But anyway, but they usually use a little omega there. If you want to call it W, I don't care. But the relationship is the linear velocity is equal to the angular velocity times the radius. Okay, so when you're dealing with any kind of vehicle, the tires spin in some rotational speed, right? The bigger the radius, the faster you go. So if you put bigger tires on a car, and your speedometer sometimes has to be calibrated to the size of the tires because you're going to go faster than it used to go when it spun. So it would have to be recalibrated. But again, a bigger radius makes for faster speed. All right? And as I mentioned before, there's your fact about revolutions and radians, and actually included degrees in there also. We already have the pi radians is equal to 180 degrees we've been using for just conversion from radians to degrees. This is the same, divide both sides by 2, you get here, right? But one revolution, it's better than going half a revolution equals pi radians equals 180. So it's just easier to go with it that way when we're dealing with this. So looking at that, and that's the facts. In general, when you get a problem involving this, it's going to sound like this. The wheel spun at this many degrees per hour. How fast is the vehicle going in miles per hour? All right, and then you just, they're going to tell you this and maybe this and ask you for that. Or they'll tell you this and ask for that. So, you know, they'll tell you 2 and ask for the third. But then they always ask for a specific unit, so then it becomes a glorified unit conversion problem. Once you get the correct unit, then you're going to have to convert that. Now, one thing I want to mention to you is, of these 3, degrees, radians, revolutions, your best friend is radians. All right, radians can be dismissed if you don't need it, and it can be put in if you do. So in other words, if I start off at an angular velocity and I'm trying to get to a linear velocity, I'm going to have an angular unit in my problem. The angular unit I want in my problem is radians, because I can just say, okay, radians, thanks, I don't need you anymore, go away. All right. Or if you start off with linear velocity and radius trying to get an angular velocity, you need an angular unit on there. You're going to get to a point where it's nothing per second or nothing per hour. Then throw in radians, now you got an angular measure. So if you need a unit of angular measure in there, radians can go in. If you don't need a unit of angular measure in there, radians can be pulled out. Okay, it's just free. All right, so if you need it, great. If you don't need it, great. All right, it's just very easy to get along with. So that's our way of getting out of one into the other. So a wind machine is used to generate electricity. The wind machine has propeller blades that are 12 feet in length. If the propeller is rotating at 3 revolutions per second, what's the linear speed in feet per second of the tips of the blade? So the question, what is the linear speed in feet per second? That's our goal. So V is what we're looking for, and we're looking for a unit of feet per second. So that's the first place I'll look at here. I'll get to you in a minute. So, linear speed is what I'm looking for. So, you've seen these wind machines down near Petersburg, right? I think they got longer than 12 foot length, about 150 or something. I don't know, they're really long. Anyway, but you got this. So you got this thing in the middle that's rotating them, and then you got these blades here. That's pretty bad. Anyway, it's spinning in this direction, right? And they don't look like they're moving very fast because they aren't. They're just kind of like this. The question is, how fast is this point moving? All right, so that point happens at the end of the radius. All right, and the speed at which it's turning in a circle is propelling that point in a linear fashion, but it's staying on there. But if imagine that if it were a piece of water, like a piece of ice or something, and it's spinning around, and it became disattached, it would launch in a linear fashion like that, right? So, with that in mind, anytime I'm looking at angular linear speed, I'm going to go immediately to my V is equal to R omega formula. And I want to identify what I know. What I know is the radius, and what I also know is omega. So the radius is 12 feet, and omega is 3 revolutions per second. All right. Very important, put units in these problems. Again, it's a glorified unit conversion problem. They need to be there. All right. The angular speed's in revolutions per second, and again, my best friend is radians, so there's going to be some conversion of radians involved there, and you'll see why in a second. But this is always the formula I use, and I'm trying to find V, so I'm going to get V equals 12 feet, which I'm going to put over 1, times 3 revolutions per second. Okay. And the type of unit you're going to get initially on these linear velocities is going to look like this. When I multiply those out, I'm going to get 36 foot revolutions per second. Unless you're already in radians, then you can throw it out right away. But if you aren't, that's what you usually get. Foot revolutions per second, foot degrees per second. You're going to get some unit of length and unit of angular measure together. Okay, the angular measure is the one you don't want to have because, again, feet per second is what we're looking for, right? There it is, but this revolution is being pesky and hanging around. We don't want that. So I want revolutions to go away. And again, I want to convert to radians. Because again, radians can be dismissed as I wish. So 2 pi radians equals 1 revolution. Now the unit of revolution on top and bottom cancel each other out. And again, the unit of radians, I don't need it, so I can throw it out. Okay, so again, it's a very friendly unit. If you need it, go ahead and put it in. If you don't need it, take it out. All right, I don't need it, so I take it out. What I'm left with numerically is 36 times 2 pi. Which comes out to 226.19 feet per second. And that's exactly what we're looking for is feet per second. If it happened to say miles per hour, once I get to feet per second, now I got to convert feet to miles and seconds to hours. So again, you have to get the unit they're asking for. Sometimes it's that simple. Other times, you know, if you go to miles per hour, 5,280 feet in 1 mile, and 3,600 seconds in 1 hour. Then you'd have to do the 226.19 times 3,600 divided by 5,280, and just like that, 154 miles an hour. And just kind of think about that.
That's pretty.
3 revolutions per second. It's spinning pretty fast. I mean, it's going 3 times around in a second. All right, but 12 foot long, 150 whatever miles per hour. That's pretty fast. All right, so kind of amazing those turbine things.